Large-scale atmospheric cells in the Coriolis effect redistribute large amounts of energy in relatively predictable manners, but they also generate another major aspect of climate, the winds. And there are patterns to where the winds blow that alter climate dynamics throughout the world. In addition to the large cells that we talked about, there are additional components to circulation patterns. For example, what are called the prevailing winds. And these are winds that have a relatively frequent direction in a given spot, the most frequent wind directions. Here's a figure that we saw earlier that I had blocked out the middle of. And when we look at the middle, we can see the general patterns of winds at the global scale. So for example, the equator right here is labeled ITCZ, which stands for the Intertropical Convergence Zone. These are the areas where, on a global basis, we have a lot of rising air. But in addition to have rising air, we tend not to have a lot of horizontal winds. And so this is an area that's often called the doldrums, because there just aren't general winds that are blowing east or west. When we look here, roughly at 30 degrees, these are the areas where the winds descend, and this is a subtropical high pressure. South of that, at least in the northern hemisphere, the cells are starting to turn a little bit, and you have what are called the northeast trade winds. And these are areas where typically you have easterly winds. In addition, if you look to the north of the subtropical high pressure, these are areas where you tend to have westerlies. And these are winds that typically blow to the west, even in the southern hemisphere. So roughly at 40 degrees, it's an area known as the Roaring Forties, areas where you have relatively strong westerly winds that are pretty consistent. The causes of these general patterns of winds are the large cells that we talked about, such as the Hadley cells. Here in red are shown relatively low elevation winds. This is the area of the atmosphere where air tends to rise and then moves north and rises in elevation. Where it descends, north of that you tend to get the westerlies, south of that you tend to get the trade winds as that air tends to cycle back and move in a relatively easterly direction. The Coriolis effect is at play here again. The authors state that at the boundaries between the major cells of atmospheric circulation, relatively sharp gradients of temperature and pressure, together with the Coriolis effect, generate strong winds over a broad height range in the upper troposphere. These high elevation winds are often referred to jet streams, and they can control climate on a multitude of scales. In addition to these broad patterns, latitudinal patterns, there are regional patterns. So the authors state that the uneven distribution of land and the ocean on Earth's surface creates an uneven pattern of heating that modifies the general latitudinal trends in climate. What's important here is that it's relatively uneven. The patterns that we set up are general patterns, and they're modified by a whole host of other factors. What's important to know here is that air over land warms more than over oceans, and that generates some of the regional patterns that we see in winds. In addition, ocean currents move heat, and there are a number of ocean currents that are redirecting large amounts of energy and altering the regional climate. Lastly, land is distributed unevenly, and this generates characteristic patterns of rising and falling air, low pressure systems and high pressure systems, altered patterns of winds. This uneven pattern of land across the Earth sets up additional cells that become characteristic features of the climate in different regions. So for example, what's shown here is a pattern that you typically see in January. So for example, what this shows is that there are low pressure systems that tend to set up, for example, in the northern Pacific. This is referred to the Aleutian Low. And you can see that it moves in a counterclockwise direction that's associated with rising air. In contrast, there are high pressures that system that's set up in the more in the equatorial Pacific and over North America. Another low pressure system here over Iceland is known as the Icelandic Low, while the Bermuda High also sets up quite often in January. If you take a look in the southern hemisphere, there's a whole host of high pressure systems that set up. And again, these are areas of descending air that are relatively cold, relatively dry. If you also notice, here's the ITCZ, the Intertropical Convergence Zone, which is shifted slightly south of the equator. And again, this is going to be an area where you aren't going to have relatively strong winds. It's going to also determine the boundary between the two major cells that are setting up, the Hadley cells. In contrast, in July, there's a different pattern of high pressures and low pressures. Here in the southern hemisphere, we see these really strong winds that are setting up roughly at 40, 50 degrees latitude. In the northern hemisphere, there's a high pressure system that sets over the Pacific, and this is known as the Pacific High, and that low pressure system sets up off the coast of California. The Bermuda High here sets up in the Atlantic and had shifted a little bit westward from where it was in January. And this Bermuda High, for example, can shift over southeastern North America and change the patterns of circulation over there, setting up relatively consistent drought conditions over the southeast, for example. In addition to these patterns of high pressure systems and low pressure systems, intertropical convergence zone, trade winds and westerlies that set up, there's also what's known as planetary waves. And these planetary waves alter the climate in slightly different manners. When the prevailing winds hit the land, they tend to go up and down based on the topography. The authors liken it to standing waves in the rapids of a fast-moving river that are governed by the location of rocks in the riverbed. So as these waves hit land, they're going to often hit mountainous areas and are pushed up, and then they fall back down, and that sets up a planetary wave, much like if this was a rock in a riverbed. Now there's consequences for that too as far as local temperatures are concerned, with differences in what you see in the trough versus at the ridges. The authors state that temperatures are comparatively low in the troughs, and that's because when you set up that system that works like this, and this is your trough, that tends to bring in air from the north, which is relatively cold. In contrast, the temperatures are comparatively high in the ridges, and that's because you tend to get more southerly air and warmer air, at least in the northern hemisphere, that gets pushed up and warms the higher areas to a certain degree. Overall, it's important to remember that climate is not static. There's a lot of shifting that happens of these large-scale cells, prevailing winds, high and low pressure systems that occur throughout the year. In addition, climate spatially does not vary smoothly. There's a lot of variation that's generated by a number of factors. Ocean currents, the distribution of land, for example. All of these make climate a very dynamic system and spatially heterogeneous. There are patterns, general patterns that get set up though, and it'll be important to keep these in mind when we're thinking about the climate of systems and then the functioning of those ecosystems.